Let's see. So we're going to talk about data structures today, which is a fun topic. We've seen a couple of data structures so far, like red-black trees and 2-3 trees and B trees. Today we're going to see a bunch more, and throughout the class we will see several more. We're going to start thinking more about how do we design data structures that do the things we want to do, and what techniques are there for designing data structures. And today we'll talk about one technique, and I'll start out with an example and then tell you what the technique is. So this is something that we know about order statistics, but now dynamic to a data structure. So the dynamic order statistics problem is you want to maintain a dynamic set. Let's call it S. Subject to some operations. In particular, the set is dynamic, so there's going to be insertions and deletions into the set. But the interesting operations we want to support are like order statistics. So OS stands for order statistic. One thing we want to do is be able to find the ith order statistic. Okay, find the ith smallest element. Okay, that's just like select, except now the set of elements that we want to be able to find the ith smallest element in is changing dynamically. Okay, something else we'd like to do is called rank. And this is sort of the inverse of the select operation. So if you give me some element x in S, I want to know the rank of that element. Who remembers what the rank is? This is from a few lectures ago. Someone tell me the definition of rank. Too early in the morning to remember? Way back. Yeah?
It's like position if everything were ordered.
Right, it's position if everything were ordered. So position in the sorted order. Good. So it's just like the inverse. Okay, it's this I. Cool. So that's our first goal. This will be, how can we make a data structure that you can insert and delete elements and be able to quickly solve these kinds of queries on that set. Okay, instead of just searches, we want to do selects and ranks. And the way we're going to support this data, these operations, is to use a red-black tree. Okay, so we're going to build on the operations we had, or the data structure we had before. So we have this set S. We'd like to be able to do insertions and deletions. So let's store them in a red-black tree. That's sort of the most sophisticated data structure we know so far. We could also use 2-3 trees here. That would be fine. But I'll use red-black trees. And we need some more information. Okay, it's hard to find the ith element in a red-black tree just walking from the root down. It's easy if you have some extra information. So the extra information we'd like is the subtree sizes. So at every node, we're going to store the size of the subtree rooted at that node. Okay, and I'll use some notation for that with the vertical bar. Okay, so I'm going to write the key of the node, just like in a red-black tree, in the top half of the node. And I will write the subtree size in the bottom half of the node. Okay, so every node will store two things in addition to the usual set of pointers. Okay. Let's do an example. So here's an example of a tree. I won't bother coloring the nodes red and black, but think of this as a red-black tree. And my set of keys here is the letters in the Latin alphabet. And you know the sorted order of the alphabet, I'm sure. But just so we can distinguish what's a subtree size and what's a key, I'll use different universes for them. And the invariant that we have here, I'll write it back on this board. So I want to store the subtree sizes of every node. What is the invariant that tells me how the size of the subtree at one node relates to other things that we know? This is from a problem set like 3 problem sets ago. Anyone remember the invariant on subtree sizes? Yeah. Of the children? Right. Yeah. The subtree size of a node is 1 more than the sum of its children's subtree sizes. Good. Should look familiar. Size of x is size of left of x plus size of right of x plus 1. Okay, and you can check that. This is useful because it's actually sort of an algorithm. If I want to know the subtree size here, I just add up 5 and 3 and 1, I get 9. Okay, and in general, you can check these are the subtree sizes. There's 3 nodes down here, there's 5 nodes here, 3 nodes over here, and 9 nodes total. Okay, so that's what we want to store. Okay. Now the question is, now we have this. Suppose that we have all these subtree sizes. How can we do a select? Okay, so that's what I'd like to do next. What does the select algorithm look like? First, I want to mention one implementation trick, which will make dealing with the end cases easier. I mean, this is something I sort of mentions for red-black trees. Okay, the nil pointers, which I haven't drawn here, each of these nodes, wherever it doesn't have a child, it's actually pointing to a node called nil, and that's called a sentinel. You can also think of it as a dummy node or a dummy record. Okay, and that will store the nils. So one neat thing, which I didn't mention when I was talking about red-black trees, is that you can actually just have one node that's called nil. And everywhere where you don't have a child, you point to that one node. Okay, something like this. I won't draw on the whole thing because it's a real clutter. You can just have one node called nil, and that will allow you to deal with your boundary cases. And in particular, we should define what the size of nil is. So what's the size of nil? 0, right. I knew a professor once who, whenever he asked a question, the answer was 0. Okay, I think that will come up later. See if you remember. Okay, so now how do we do select? Okay, OS select, okay, it should still be written up there. We're given some, okay, I've changed the notation here. So I'm going to reparameterize somewhat so that I can get a recursive algorithm. Okay? And I won't worry about the set S. What this means is I want to find the ith smallest element and run into lines in the subtree rooted at x. Okay, that's going to be useful for my recursive algorithm. And S, the dynamic set I'm dealing with is implicitly around here. Okay, so here's the algorithm. I'm going to need some space. Does anyone recognize these last 4 lines? Should look familiar. Again, you have to think back like 3 lectures, 4 lectures. I equals k if I is less than k. Go down the left subtree. If I is greater than k, go down the right subtree. Yeah?
Like search?
Select, yeah. These are like select. In fact, I think they're exactly the same as select. So what's going on here? I want to find, so I have some node x, and I want to find the ith smallest element in the subtree rooted at x. Well, x has a left child and it has a right child. And they have, and we assume now that for every node we know its size. So I can say, well, that means I know how many nodes are off to this side. I know how many nodes are smaller than x. And if I want the ith smallest, and there's at most I guys in here, then I know the ith smallest is in here. And if there's many more than I guys in here, I know that the if there's many fewer than I nodes in here, I know that the ith smallest is in the right subtree. And if I'm really lucky, this guy is the ith smallest. And that's the case when the size of this subtree is 1 smaller than I. Okay, and that's what this is checking. Take the size of the left subtree, add 1. If we get exactly the ith, which is what we want, then we're lucky. The root of the tree we're looking at is the ith smallest. Okay, but it's just like the select algorithm we had before, except instead of having subarrays, we now have trees. And we're storing the sizes of those trees. Okay, so let's do an example here. So let's suppose that I want to select the 5th smallest element in here. Okay, so I'm starting with the root, and I want the 5th smallest, so I equals 5. Okay, so what's k for the root? 6, right? K is 1 more than this value, the size of the left subtree. Okay, this is a fast algorithm. I don't have to go through and count the number of nodes down here. I've got it stored right here. Okay, so which way do I go? 0. Right, left. Good answer. So 5 is less than 6, I go left. Okay, so I go down here. And what's my new value of I for the recursion on the left side? 5, right. The difference is 0. Okay, slightly more sophisticated. And now what's the value of k? 2. Thank you. Right, I doesn't change because I haven't offset by anything. When I go left, I doesn't change. K is now just one more than the new left subtree. So which way do I go? To the right. Because now 5 is bigger than 2. I is bigger than k. So I go down here, draw arrows. Now what's I? 3. Right, it's the difference between these two. 5 minus 2. And k is again 2. And now which way do I go? Right. I is bigger than k again. Now I'm down here. I equals 1, I hope. 3 minus 2. And k, well, now we're done. Right, there's no left subtree. But we use this implementation trick, so this code doesn't break, fortunately. We take the size of the left subtree. That's a nil. The size of that is 0. So k is actually 1 here. Okay, and then we discover, by this nice trick, that I equals k. And we're done. So this, I claim, is the 5th smallest element among these letters. And you can check the in-order traversal A, C, D, F, G, H. That's the 5th smallest. So it worked. Good. Is that algorithm clear to everyone? Okay, what's its running time? Sorry? Logarithmic, right. Because we're spending a constant amount of time at each level. We just walk down every step. The height of the tree is logarithmic if we're using a red-black tree. And so it's order log n. The time is proportional to the height of the tree. And that's order log n for a red-black tree. Or for any balanced tree. Again, we could use 2, 3 trees, but it will work out a little differently. Okay, so this is a fast algorithm, right? How long did select take? Our original algorithm for this problem. Order n. Yeah, it took linear time. So this is exponentially faster. Okay, this is really fast. Compare n to log n. Log n is way smaller, as you know. It grows smaller than any polynomial. So this is cool. It's saying if we can sort of pre-process our data and put it into this nice tree, we can do select operations really fast. Okay, now to build this tree probably took at least linear time, n log n if we're going to sort it. Right, so that, okay, it took n log n time to get this set up. But now that it's set up, we can do this select operation really fast. If I want to find the 5th smallest, and then the 10th smallest, and then the 25th smallest, I can do each of those really fast once I'm set up. There's log n per operation. So this is sort of the central idea of pre-processing and making data structures to do things faster. Okay. The other operation we need is OS rank. I won't talk about that here. Okay. Read the code in the book. It's similar. It's not hard. You just walk up the tree instead of walking down. Okay? Good. So we had this sort of central idea that we should store the subtree sizes in the nodes. Okay, why don't I leave that up? The question is, why did we store the subtree sizes? We want to understand what was going on here. This worked great. So why did it work so great? Okay, one natural thing, instead of storing subtree sizes, we want to know about ranks, ultimately. We want to know where things fit. So why not store the rank at every node? Okay, we stored subtree sizes, but subtree sizes are somehow not what we want. It worked out in the end, but wouldn't it be more convenient if we stored ranks? You know, this is the first element, this is the second, this is the third, fourth, fifth, sixth, seventh, eighth, ninth. Why can't I just store those numbers in those nodes? Do you have an idea? Right. When you do insertions and deletions, you've got to do a lot of work, whereas, so you can finish.
Yeah, well, whereas this way, when you do insertion and deletions, you can kind of look at the number of like children.
Okay, we'll get there. Yeah, exactly. So the answer is updates are costly. Okay, if I stored the ranks, whenever I made a change to this tree, I'd have to change pretty much everything. If I did an insertion over here, if I inserted a new thing that's smaller than A, like 9, if that's in ASCII. All right, I should use a better. What's a good punctuation character that comes before A in ASCII? Capital A? I don't know. What's ASCII code 64, for example? No one knows? Come on, it's supposed to be geeks. Sorry? Lowercase letters. Those are larger, believe it or not. Well, you don't know your ASCII tables. All right, I don't know. I think dot. Let's do dot. Just if you insert something smaller than A, I have to change the rank of every other node goes up by 1.
Control characters.
Control characters. OK, Control A. Yeah. That's a good one. That's ASCII code number 1. I know that. OK, so I don't want to have to store the ranks because it's really expensive to update them when I do an insertion. That's the idea. Okay, it's hard to maintain these values. I've assumed so far that we just know them. So I've actually cheated a little bit, but I haven't told you when the tree's going to change whenever I do insertions and deletions. So how do I maintain the subtree sizes? I say that I can't maintain the ranks, but that's sort of a negative statement. I want to maintain something. I claim that I can maintain subtree sizes, and that's why we store them instead of ranks. OK. So what I need to do, there are two kinds of modifications. There are insertions and there are deletions. Those are the kinds we're talking about. Okay, we know how to insert and delete into a red-black tree and maintain balance and the nice coloring properties and all this. The question is, how do we maintain this new information, the subtree sizes? And we hope that it doesn't take us too long to do that. So let me go to another board. Oof. I'm afraid we lost a good eraser. So you have a ghost of the previous blackboard. OK, so how do we do this maintenance? There are several components to what we need to do. Okay? When we do insertions, we add a node. That makes a change. There's also rebalances. So in particular, when we're just adding in the node, when we're inserting a node or deleting a node, that causes some changes. And it's actually pretty easy to update the subtree sizes there. Both of these operations walk down the tree. And it turns out as you walk down the tree, you can tell what changes you should make. Okay, so let's look at an example. Perhaps I want to use the same example. It's getting a little messy. Why don't I redraw it? Okay, so let's say m 7, C5. Okay, this is exactly the same as before, except now I'm leaving some space in these entries because they're going to change. Did I miss? M is 9. Oh, boy. Thank you. H is 1. P is 3. N is 1. And Q is 1. Okay? This is a very poorly drawn 9. So let's suppose that I'm inserting K. Okay, well, just practice your alphabet. K falls to the left of M, so we go down this way to insert. Well, that means we're going to be inserting into the subtree, so we better increment this count. It's going to end up 10. So I can do that now. Okay, that's a change. I'll highlight the changes. Now we're in this subtree with C. K falls to the right of C, even though it usually sounds the same. And we go to the right. Okay, but in particular, we're going to be inserting into the subtree, so it should increment this count 6. Okay, that's another change in the sizes. Now there's F. We fall to the right of F, so we're going to go down here. But on the way, we'll increment this value to 4. And finally, we get to H. We'll increment its value to 2. And then we add on a new node, which is K. And K will have its initial subtree size of 1, because it's a leaf whenever we insert a node. Okay, so these are the changes that go on in the beginning of an insertion or deletion. But an insertion and deletion does more, right? It rebalances. So we need to say, how do we deal with rebalances? Okay, so we also have to maintain the subtree sizes while we're rebalancing. So we're going to follow through. Rebalancing breaks up into a sequence of steps. Each step is either recoloring or rotation. And for each kind of step, we're going to say how to maintain the subtree sizes locally. And that will be enough. If we can do it at every step, then we maintain it all the way through. Okay, so how do we maintain subtree sizes when we recolor a node between red and black? You heard. It's cheating. Professors aren't allowed to answer. Nothing? Right, 0. That's what Professor Lyserson said. Okay, this is good. Recurring theme. There's no effect on the tree. So I don't have to do anything. Subtree sizes don't change. So that's easy. Rotations are a little bit trickier. So what I'm going to do, the key thing about what I'm going to do is that it's local. I can fix up these subtree sizes locally in constant time. This is where we win. This is cool. So let's say we're doing some rotation. And say we have some node E that we're doing a rotation on, and we're doing a right rotate. So I care about its left child. Okay, that's sort of a local picture of a tree. These are the subtree sizes again. Now, if I do a right rotation, I get C at the root. C comes up, E falls down. Okay, and these subtrees are hanging off just like they used to. Except now these numbers are wrong, so don't write them down, sorry. Should erase them. The new picture. Well, to figure out what these subtree sizes are, I need to know a little bit more information. So it depends how many nodes are hanging off these subtrees. So let's suppose I have 7 hanging off here, 3 over here, so that adds up to 10 plus 1 is 11. And let's say I have 4 over here, so you add it to 11, add 1, you get 16. Okay, these subtrees are going to hang off just like they did before. And so it's pretty easy to figure out what the subtree sizes of these nodes are, right? What's the subtree size here? 8, right? 1 more than 7. And here, 16, right? I can double check. 16 should be the right answer because we're just adding up the total number of nodes in this tree. I haven't changed the number of nodes, just done a rotation. So it should still be 16, like it used to be in E. Okay, it moved over to C, because C is now the root. Okay, so this is very easy. I'm applying, I don't think I have it anymore, this invariant that says the size of a node is the size of the left subtree plus the size of the right subtree plus 1. So as long as I can keep track of these nodes down below the rotation, in constant time, I can update the nodes that moved. Okay, nothing else changes above here. Just 2 sizes change. Okay, that's great. It's purely local. And so that means insertions and deletions are still fast. They're still logarithmic time. Okay, with red-black trees, they were logarithmic. And now I claim that I can maintain these subtree sizes and not make insertions and deletions take any longer. They still run in logarithmic time because each time I do a rotation, which costs constant time anyway, I spend another constant amount of time fixing up the subtree sizes. Okay, so it's still, I'm only increasing the constant in the running time. And this is now a complete data structure, right? Now I have dynamic order statistics. So I said how to do insertions and deletions. Okay, deletions are similar. I said how to do insertions. I mean, deletions also boil down to rotations in the end, so that's good. So I can do updates and now maintain this new information, which is the size of each subtree. And then we saw how to do select here, and rank is similar. So we're done. Now we have all these great operations. Good. Any questions about dynamic order statistics? These are called order statistic trees, I guess. They're pretty powerful because if you have rank and select, you can do things like, well, I have this element x. What is the 25th element after element x? Okay, which is, if you store the elements in an array, it's really costly to do insertions. With trees, it just takes log n time. Okay, so that's cool. All of this takes logarithmic time. And this kind of data structure that we developed is an example of a more general principle called augmentation. So let me tell you what the general principle is, because it's really useful. This is sort of a major technique for designing data structures, because it's usually a lot easier than building a data structure from scratch. Okay, let's call it a methodology. It sounds cool. All right. Long words. Good polysyllabic word like polysyllabic. Okay, and as we run through the methodology, I will put in parentheses the example that we've just seen. Okay, order statistic trees. Okay, the methodology is in essentially 4 steps. The first step, this is pretty, get some good chalk here. Sorry. It'll get going, you think? Oh, yeah, that's good. So the first step is to choose an underlying data structure. So you all know what the word augmentation means, right? Change, I guess, internally. Increase Sometimes, yeah, it's sort of a vague definition. How many people played Rogue? No one's played Rogue. Wow, you've played Rogue. I know. I've seen you play. Wow, am I that old? Boy, I used to play Rogue, and you can get this potion called the Potion of Augmentation. I could never figure out what it did, and reading the dictionary did not help. Okay, but when it comes to data structures, I know what they do. I gave away the answer here. So what we were doing with these order statistic trees is starting with the red-black tree. We built up from that. Okay, that was really useful because red-black trees had a lot of machinery. It said all you need to do is say how to do rotations, and then you're done. Okay, so that's cool. That's the idea of augmentation, is you build up from a data structure you already know. Okay, the second thing you need to do is figure out what other stuff you need, what other information. Okay, call this additional info. And the idea is that, well, in every node or every record or whatever in this data structure, we can store additional information. Okay, so what did we store here? Okay, it's obvious. We stored subtree sizes. That's what we added. And that allowed us to do more operations, new kinds of operations efficiently. Okay, the next thing you need to do is verify that you can actually maintain that information. Right, you have to say, well, when I do an insertion or a deletion or any kind of update, I can still maintain, so we'll call these modifying operations like insertions and deletions, in the old data structure. Whenever I have those, I can still maintain the subtree sizes in this example. So in the example, order statistic trees, I needed to deal with insertions and deletions. And the key with those was that I could do rotations. Okay, because basically all the restructurings of the tree boiled down to rotations. There was a little bit extra when I actually added a node. I added a new leaf up here, and so I had to update these counters. But that was pretty easy. Right, this is sort of the heart of what's going on, that I can do this local modification and maintain this information in no more time than I had before. So it didn't slow down my data structure. And the last thing is, well, now you have this new information, this additional info. Now you can build your new operations that you want to do. Okay, and build a better data structure. More powerful data structure for doing additional operations. And, geez, these disruptive people in class, come on. That was Professor Leisterson. Okay, good. So in this example, we wanted OS select, order statistic select, and order statistic rank. Cool. So those are the 4 steps. But these are not really sequential steps. Okay, so it's not that you do one just completely out of the blue, and then you decide, OK, well, now I'll think of some new information I'd like to keep. And then, OK, I'll check, oh, yeah, I can maintain that information if I'm really lucky in step 2. And then, well, maybe I can do something useful with them. OK, so that's not how it goes, right? All of these things interact. So I have in mind what operations I want to do. I think what information might be useful. Can I maintain, subject to being maintainable quickly, what info should I store? And then, and then implicitly you think, well, what's the data structure that most closely matches what I want to do so that I can maintain this information and it will do what I want? Okay, so all of these things are mixing together, but this is sort of like a checklist. Okay, what do I call it here? Guidelines. That sounds good. You don't do 1, then 2, then 3, then 4 completely independent of each other. But it's a good checklist. You have to do all 4 of these things to make sure that you're done. Okay. So we're about halfway through the lecture. And the rest of the lecture will be about another example of this methodology. Okay, so we're going to use these ideas to build a new data structure called interval trees. So this is going to be fairly different from what we've seen before. Okay, so what do we want to do? I want to maintain, usually we maintain numbers. I'm going to maintain something different. I'm going to maintain intervals. So I have a dynamic set of intervals. So that means I'm going to be inserting and deleting intervals. And I want to be able to do queries on them. But I mean, you all know what an interval is, right? Something like 7, 10. Okay, this is called, let's call this I. The notation for an interval is something like this. So this is a closed interval between 7 and 10. But this is the real line, the x-axis. Okay? So I'm going to call 7 the low coordinate of I, or the low endpoint, and 10 is the high endpoint. Okay? Normally you would call this the left endpoint and this the right endpoint. But we get confused between left and right. No, that's not the reason. In red-black trees, or any kind of tree, we're always talking about the left child and the right child. So if we use left and right here, we get confused. Okay, you'll see why. So this is low and high. Easy enough. So let me draw a picture here. I want a running example of a set of intervals. So this is 5, 11, 4, 8. 8 will end somewhere here. 17, 19, 15, 18, and then 22, 23. Good. So that's a bunch of intervals. I mean, really, these are all on a line, but I'll separate them out so that you can see where they are. And now we want to support some kind of query on these intervals. Okay, fine, you can insert them and delete them. That's not very useful. Okay, it's very easy to just insert and delete intervals. It becomes interesting when you can ask some queries about all of them together. So suppose I give you another interval. Let's call it the query interval. Say it's I. I is the right word, yeah. I would like to find, so I give you some other interval here. I want you to tell me whether there are any intervals that overlap that interval. Okay, and if so, find one. So find an interval that overlaps I. Okay, you all know what overlap means, right? These two intervals overlap. These two don't. Okay, they share a point in common. I'm talking about closed intervals here. You could deal with open intervals. Those are just some special cases. Okay, I'll only talk about closed intervals, but you can have clopen intervals if you want. It doesn't change this question too much. Okay. So this is a sort of a global thing. I give you an interval in the middle of nowhere. Somehow you've represented the set of intervals. Do any of them overlap? Does the one that you just considered, I, say it's here, does it overlap anything? I sort of want to roll it up and down and see whether it hits anything like this interval. Okay, I want to do the queries fast. Okay, so let's follow this methodology. I want to build a data structure to do this using data structure augmentation. So the first question is, choose an underlying data structure. So does anyone have an idea what data structure we should use to store these intervals? And this is a dynamic set, so we should probably use some kind of dynamic set data structure. I mean, don't know too many. Sorry, 0.
Binary search tree.
Binary search tree. Yeah, that would be good. And it's got to be dynamic, so we need some kind of dynamic binary search tree. I mean, we could just use plain binary search trees, but then we're not guaranteed that they run fast. If you have a bad sequence of insertions, you could get a really tall tree. So we could use order statistic trees. Sure, that'll work. But we won't need order statistics, so I'm just going to use red-black trees if you don't mind. Okay, but you could substitute in order statistic trees. That would work too, because in particular they do all the red-black stuff. Good. Okay, so these numbers will refer up to that board. So I'm going to use red-black trees again, because they're pretty versatile. Versatile, that's right. They're universal and they're versatile, so that's good. Red-black trees need a notion of order, right? So that's cool. I mean, red-black trees will support insertions and deletions. If I want some kind of useful binary search tree structure, the things I'm inserting have to be ordered. But intervals are not ordered, obviously, right? It's clear that 710 comes before 1719. But for something like 710 versus 511, I don't know. I guess this one's sort of to the left a little bit, looks like. So any proposals on how we should, red-black trees need keys to be sorted. So for an interval, we should define what the key of an interval is, and that will define an order on them. So any proposals for what kind of keys we should use? Yeah? The low number. Good. Any other proposals? Yeah? The average, like the midpoint. Yeah? I guess the other option is the high number, right? There aren't too many things you can do with an interval. The first proposal was correct. Okay, so we'll use on the low endpoint. That's what we'll use as our key. Okay, I was expecting people to say midpoint first, because that's sort of the obvious thing, I guess. I mean, why choose the left or the right? It's kind of asymmetric. Why not choose the middle? And then sort by the middle. Okay, but it turns out the middle doesn't give you useful structure. Okay, whereas the left endpoint gives you very useful structure. Or sorry, the low endpoint, I should say. The high endpoint would work just as well. Just reverse everything. Okay, but it will be useful for us to be asymmetric in this way. The second thing we need to do is say, what additional information do we need? Okay. So each node is going to store this key, the low endpoint. That's what red-black trees do. But we're also going to store the interval that it's about. So if we have some node x, it stores the interval associated with x, right? Every node stores an interval. Okay. It also stores a key, but that's just the low endpoint of the interval. Okay, I sort of have to say this because red-black trees just store keys. I have to add in this, but that's no trouble. So those don't change. It has to store more. And let's see. I don't think you can guess this, so I will say it. We're talking everything about low endpoints, but we're going to need to know about high endpoints as well. Otherwise, we don't know where our intervals are. Okay, so we're also going to store in each node the largest value, the largest right endpoint, the largest high endpoint, sorry. That'll be called M of x, M for maximum, in the subtree rooted at x. Okay, so let's do an example. Okay, so I should give you some notation. When I draw a circle, that's a node. And we'll split it so that the interval of x is on the top and m of x is on the bottom. Why don't I draw the tree? Okay, so this is a red-black tree. Why don't I put in colors? I didn't do this last time, but let's do it now. Okay, and I want that set of intervals. Okay, so let's say, I put 17, 19 at the root. I'm sorting by left coordinate. Okay, so 5 comes before 17, 4 comes before 5, 15 comes in between 5 and 17. So 15, 18 goes here, and 7, 10 goes down here. And the largest interval is 22, 23. Okay, so that's the basic structure without this additional m information. That's just storing the interval at every node, sorted by the low endpoint. Okay, now I want to compute these m's. So it's just the largest value in all the intervals in the subtree rooted at a node. So in a leaf, there's only one interval in here. So the largest value here is 8. Okay, here it's 10. Here it's 23. Those are the m values. Now here it gets a little more interesting. What's the m value? 18, right? Just the max of 18 and 10, I guess. Here should be also 18, because this has smaller values. And here, what's the answer? 23. Good. So those are the m values. Just take the max of everything below you. Sorry? Plus yourself, right? Everyone in the subtree. So that happened here, I guess. Took the max of my 2 children. I only had 1 child. That was 10. But I also had one interval here, which went up to 18. So so 18 is my max. Okay, do I want to put? Why don't I put the invariant here? Okay, just like before, we have a nice local definition of what the m value is. I needed a word out here. It's the max of things. Right? If I knew the max of my left child and the max of my right child, and I knew who I was, I can figure out the max of me. Okay, so I look at my interval and the high endpoint of my interval, int x. And then I look at my left child, take the max over there. And then I look at my right child, take the max over there. Okay, so this is like a recursive formulation of this definition. And that's useful because it's a local thing, local computation. Okay, the third thing we need to do. Okay, I think I won't have much space here. Let's go anyway. So the third thing is that we have these modifying operations. Okay, again, we have insertions, and we have deletions. We have to say how to maintain this m value without slowing us down much. So let's think about an insert. Inserts will be very similar to what we had before. We can update things on the way down. We're adding a new leaf when we insert into a red-black tree. So I don't know, let's say we insert someone here. Okay, so this is a guy we're adding. And his value, I don't know, 20, 50. The max here is 50. Okay, so I want to add this node. So to figure out this is where it goes, I went right from here, went left from here. Okay, because 20 was bigger than 17, smaller than 22. Well, on my way down, I can see, well, this guy has a right endpoint of 50. So I better update this to 50, because it's bigger than it was before. And I'll update this one to 50, because it's bigger than what it was before. So on my way down, I make those updates, but that's all that changes. Okay, no other nodes, no other m values change. So that I can do just on the way down. It slows me down by a constant factor, no big deal. Okay. The other thing we do, sort of won't worry about deletions. Deletions are similar. The other thing we do during insertions are rotations. And there again, I want to do a purely local fix-up in constant time. Now, if I can do that, I'm done. Right? I can maintain this new information throughout all my updates without any overhead. Okay, so let's look at an example of that. Okay, what I care about are these two nodes. So I've drawn them in full. These ones, the subtree's hanging off here. All I care about is what their m values are. Okay? So right rotate, we'll bring this node up and this node down. So we'll get 620 at the root and 1115 in the right subtree. And then we have the same subtrees hanging off. Okay, so there's 30 over here. The m values are 30, 14, and 19. And the intervals are exactly what they were in the left picture. Now I have to update my m values. How do I do it? Okay, what's the m value of this guy? Sorry, speak louder. 19? Yeah, 19. It's just the max of 14, 19, and 15. That's what this invariant tells me. Okay, and the max here is 30 again. Right, same as it was before, because it's the same subtree that we're dealing with. So it's easy, just like before. Constant time per update, per rotation. Okay? So the total insertion cost or the insertion time is order log n, just like it was before. And deletions are similar. That's the great thing about being up here and being the prof, right? You can just say, deletions are similar. Don't worry about it. Same deal. Okay, the main thing is rotations. There's a general theorem which I will mention, which is kind of cool. Whenever you want to maintain some new information, like m or subtree size, and it only depends on your left child and your right child and you, then you can maintain it in a red-black tree with no overhead. Okay, just a constant factor overhead. So you can read that theorem in the book. We've got one more thing to do. Develop new operations. Okay, that's what we really want to do. I can now erase the... Why is this information useful to us? You've probably been thinking about this for some time now. Okay, I'm doing it in order because it's easy to follow along. But if you were developing this data structure, the first thing you think is, well, how do I do my operation? I want to do these queries where I give you an interval. Tell me if there are any intervals that overlap it. And if so, give me one of them. Okay? So this will be called interval search. So let's say you give me an interval I. So usually I is an index, but for this part of the lecture, I will be an interval all the time. Okay, and we want to find, give me an interval that overlaps I, or tell me that there aren't any. So that's my goal. And here's how I'm going to do it. Start at the root. There's a loop. Say what the loop means in a second. If I hit a leaf, I'm done. The other thing is if I find an interval that I overlap, I'm done. Okay, so this is how you say that two intervals overlap. Let's say 4. Okay, this condition here in the parentheses is saying that I and the interval stored at x, int x, do not overlap. Okay, if they do overlap, this comes out false, so the and comes out false, and we leave the while loop. And then I guess we'll return int of x. Okay? So if we ever find, if we're lucky, x might be the interval we're looking for. It overlaps I, we return it. Okay. So what do we do in the while loop? Pretty simple algorithm. What's amazing is that it works. Okay, it just says, well, in one case we go left, in one case we go right. Eventually, we either find the interval we're looking for or we hit nil. And the claim is, if I ever hit nil, there was no interval anywhere in the tree that overlapped I. Okay, that's going to be the mysterious part. It will stay mysterious for a little while. Okay. So when...
probably want to return x, not into x.
Ah, good point. X might be nil.
Might be nil.
Good.
You can always get
Thank you.
into x with that
Right.
if you wanted that.
Thank you. Change this to return x. I don't want to do a nil reference. Okay, and if I want to recover the interval, I just look at int of x if x is not nil. So what's going on here? I say, well, if there's nothing in the left tree, I should definitely go right. Okay, if you work the double negatives here. If left is equals nil, this will be false, so I go to the else case. That's clear. Then the other case is when I go left. So let's draw a picture here. I have my node x. There's the left direction, there's the right direction. Okay, let's look at the m value in the left subtree. This is m of left of x. Okay, and I just put a pointer here. I compare that with the low end of the interval I'm looking at. If my interval sort of overlaps that m value, I'll go to the left subtree. Otherwise, I'll go to the right subtree. So let's look at an example. So with this same diagram, without the new node, let's say, just this. Let's say I do interval search. And I'm looking for 14, 16. Okay, do any intervals overlap 14, 16? I can cheat and look at the picture. 14 starts here, and it goes to here. So it should overlap the interval 15, 18, and no others. Okay, so let's do the search. Say, okay, start here, Does 14, 16 overlap 17, 19? No. So should I go, this is not my answer. Should I go left or right? Look at the computation. There is a left child. You can also cheat, right? 15, 18 is what I want. It's down here, so I better go left. But you can check. If I look at the max of my left, that's 18. That's bigger than 17, so I go left. Okay? Now I'm here. Does my query 14, 16? Sorry, I did that wrong. Okay, I'm comparing 18 to 14, my query. This is I. Okay, and it was bigger, so I go down here. Does 5, 11 overlap 14, 16? No. So I compare 14 with the max of the left subtree, 8. 14 is bigger than 8, so I'm going to go down to the right subtree. Then I discover that 15, 18 overlaps 14, 16. So I found the answer. Cool, huh? Let's do another example, almost the same. So suppose I'm looking for 12, 14. Okay, 12, 14, again, it doesn't overlap here. 12 is smaller than 18, so I go left. Doesn't overlap here. 12 is larger than 8, so I go right. And doesn't overlap here. That's different. So 12, 14 does not overlap 15, 18. I look at the left subtree. It has n value 10. 12 is bigger than 10, so I go this way, and I fall off the tree, and I don't find anything. Okay, it looks like we just took some random stab down the tree, and yeah, we didn't find the interval we were looking for. And let's check if it's right. So 12 starts here, and it goes to 14 here. And magically, it didn't hit any intervals, right? But it should not be at all clear that this works. Okay, and that's the tricky part, that this is a correct algorithm. Okay, why couldn't 12, 14 be stored somewhere else? We're just sorting things by low coordinate. So how do we know we're not missing anything? We're just sorting things by low coordinate. Okay, before I do correctness, I want to do a quick analysis. How long does this algorithm take? Logarithmic, right. Again, I spend constant time at each level. If I use a red-black tree, keep it balanced, then I know the running time is order log n. Cool. Here's a quick puzzle for you. What if I wanted to find all the overlaps? So instead of just wanting to find one interval that overlaps I, what if I want to find all of them? Anyone see how to do that using what we have so far? This is a little bit tricky. Yeah? Right. So some kind of recursive call. Once we find the first, if we run interval search, we find one guy that overlaps. And then, what do you want to do with it? Now you want to find the next one. But I want to try in the subtree of that interval. Well, it might be there, but it doesn't always have to be there. Okay, is there a good example of that? If I'm looking for something that strikes here, there are 3 intervals I should get. 7, 10 is down here. 5, 11 is here. 4, 8 is over here. So it did work in that case. But I mean, after I find this guy, I could keep looking in the subtree, go down here, find this guy. But then there's no one else in the subtree. I have to sort of go back and look for this guy. It's not so obvious, but you're on the right track. Find one, and then what should you do with it? Delete it. Right. This is a dynamic set. We can delete it. Then we run interval search again. Find the next guy. Delete it. And write it out in the answer. Keep going. Eventually, I don't find anyone. Then I have all of them. If interval search works. If it finds one when it can. So that's all we do. do an interval search, output that as part of the answer, delete it, and then repeat. And if you don't want to screw up your data structure, you can insert them afterwards. Right? Once you've found them all, well, you have them in your hands, you can insert them back. And then you have exactly the structure you had before. So that's pretty cool. What's the running time of this new algorithm for listing all of them? Let's suppose, what's the worst case of this algorithm? All of them are there. So that's going to take like n log n or something. That's no good. But if there are only k answers, this will take k log n time, right? So for an output of size k. Okay, I want to rub this in. This is a cool kind of bound. Okay, worst case n log n does not tell you something useful. Okay, what's important is that if there aren't too many answers, this runs fast. If there are a lot of answers, well, it runs slow because I just had to write down the answers. It's going to take me at least k time. It turns out you can do better. So there exists a data structure that runs in order k plus log n time. And in some models, that's optimal. Okay, but this is a neat kind of bound. It's called an output-sensitive bound. Okay, and you will see these kinds of bounds in your current problem set 6. Okay, output-sensitive bound, output-sensitive algorithm. It runs fast when the output is small. And that's a nice thing to capture. Okay, I need to go quickly. So we have correctness to prove. All right. Don't need the example. Okay, this is a tricky argument, so it should be fun. A claim, so look at some node x. Let L be the set of intervals in the left subtree. Of some node x, and let R be the set of right intervals. Okay, intervals in the right subtree of x. I claim two things. First thing is if the search in the algorithm, interval search, goes right from x, then the set of intervals in the left subtree that overlap I is our query interval, is the empty set. In other words, no intervals in the left subtree overlap I. Okay, that means it's safe to go right. If there's no one that I'm looking for in left, I can always go right, so that's good. The second case is a little more complicated. So suppose the search goes left. I can't say that there was no one interesting in the right. Okay, I won't show an example of that. But I can claim something about safety. So suppose I went left and I didn't find anyone. There was no I prime in the left subtree that overlaps I. Well, that's no good because I was looking for someone that overlaps. So maybe I should have gone right. Well, the theorem is if there's no one in the left subtree that you're looking for, there's no one in the right subtree either. So there was no one to find. And so it's OK. It didn't matter which way you went. You happened to go left. You could have gone right. In either case, you would have found no one. And so you're correct. OK, so what this theorem is saying is no matter which way I go, if there's anyone to find, I find them. I find one of them. OK, here, I'm definitely safe to go left because definitely safe to go right because there's no one in the left subtree. Here, it turns out if I go left, the theorem says it didn't matter which way I go. Well, sorry, I shouldn't say that. It could be that I find someone in the left subtree. That would be good. But if I don't find anyone, I couldn't find anyone anywhere, so it's OK that I went left. Okay, this is a little tricky argument to get your head around. And let me prove this theorem. So is it clear why this theorem implies correctness? It says no matter which choice I made, going left or right, it was an OK choice. Okay, I'll find someone if there is someone. So let's prove the theorem. Any questions? Good. So the first case is, well, let's suppose we go right. Okay. We have the algorithm here. When would we go right? There are two cases. We go right whenever this condition, this AND, comes out false. So it could be the left part comes out false or the right part comes out false. In either case, we go right. So the left part would come out false if there was no left subtree, if left of x equaled nil. Okay. What is L in that case? If there's no left subtree, empty set, 0. This is where I wanted to bring up 0 again. L equals 0, or the empty set. Okay? It's a funky 0. Well, so what do we want to prove? We want to prove that the set of I primes in L such that blah, blah, blah equals the empty set. It doesn't matter what blah, blah, blah is. It's empty. So that's easy. Here we don't have to prove anything. Or what we want to prove is vacuous. So what's interesting is the other case. The other reason we might go right is that this condition comes out false. So that would mean that low of I is strictly bigger than m of left of x. And a couple of brackets. Okay, this is from the code. We know this. So what's our picture? We have I is some interval here. This is low of I. And we have that it's bigger than this, which is m of left of x. Okay, so m of left of x is you look in the left subtree, you find the rightmost, or the highest high endpoint. Okay, so this is high of j for some interval j, for the sort of rightmost interval j. For some interval j in the left subtree. So let's draw in j. Right, we know that the right endpoint, the high endpoint of j, is to the left of the low endpoint of I. And we know that j is the rightmost of all the guys in L. So all the guys in L are over here somewhere. They're all to the left of I. And that's what we want to prove. We want to prove that all the intervals in the left subtree do not overlap I. This is the empty set. Okay? So we're done. All intervals I prime and L are left of I. And so in particular, they don't overlap. Okay, I'm going to erase the code, I think. I can erase the intervals. There's never enough blackboards when you want them. Okay, this proof is tricky. The second part is trickier. Involves sort of everything we've been talking about in interval trees. Okay, that was sort of obvious, right? If there's no one in the left subtree, of course you go right. Probably it was clear to you that this condition meant there's no one in the left subtree. It's part 2 that's trickier because there might be someone in the left subtree or in the right subtree. Okay, so the second part of the proof is suppose that the algorithm goes right. Okay? Left. Sorry. Just did that. That's the second case. If the search goes left, we want to prove that if there's no one in the left subtree, then there's no one in the right subtree. Well, so let's assume that there's no one in the left subtree. We assume this condition, which is sort of vertically aligned. That's convenient. The set of intervals in the left subtree that overlap I is the empty set. Okay, why can we assume this? That's the condition. If this isn't true, I mean, it could be that this is not true, but then we don't have to prove anything. Okay, so what's going on here? This is sort of a case analysis, right? If we're not in this case, we have nothing to prove, because it's just an implication. Right? So we're in the second case where we go left. There are two subcases. Either this is true or it's false. Only when it's true do we have to prove anything. Now what we need to prove in this case is that there's no one in the right subtree. OK. Well, what do we know? From the algorithm, it says we went left. If we went left, that means that condition in the if was true. That means there is a left subtree, and we have this property. So let me copy it over. We have low of I is less than or equal to m of, I forget, left of x. Okay, we know that. So what is the picture here? We have our interval I. There's low of I. We have m of left of x, and we say that that's further to the right. Okay, it's a little hard to draw the picture at this point. We don't quite know enough. Let's do what we did before. M of left of x, we know, is the high endpoint of some interval j for some j in the left interval, in the left subtree. Okay, so for some interval j in the left subtree. That's what this means. So this is the right endpoint. This is saying that the left endpoint of I is smaller than the right endpoint of j. So could j look like this? Right here, the right endpoint of j is bigger than the left endpoint of I. Could j look like this? I have to think, what did we assume? This is either too easy or too hard, or both. Both meaning for some people it's easy, some people it's hard, yeah.
No, because you're ordered by law.
No, because we're ordered by the low endpoint. Right, that's a good try, because j was in the left subtree, and so well, the trouble is I is not actually in the tree. I is our query interval. So there's no order about I. But there's something else, yeah. We assume that there was no overlap, right? This sentence here says there's no one in the left subtree that overlaps I. J is in the left subtree. That's the definition of m of left of x. So we're only looking at left of x. So in fact, J has to be over here. Right? J cannot overlap. And we know it's over to the right because the right endpoint of J is to the right of the left endpoint of I. And furthermore, everything that's in L here, we know that they're also to the right here. I guess, let's see. I don't care about L. I'm sorry. Let's forget about L. I care about J. That's what I want to prove something about. So I care about the right subtree. I want to prove that there's no one in the right subtree that overlaps I. Well, where could the guys in the right subtree be? Now we can invoke your observation.
Everything in the right subtree has to be bigger. Just hat the low endpoint has to be bigger. The low endpoint of j.
Right. Has to be bigger than the low endpoint of j, right? So j is over here in the left subtree somewhere. Here's x. Anything in the right subtree, by the binary search tree property, everything in here has a smaller key than over here. So as you said, every I prime has a larger left endpoint than j does, because j is in the left subtree. Okay, and j was just some exhibition of the max. Okay, this is tricky. That means we have that the low endpoint of I prime is at least the low endpoint of j for all for all I prime in R. Whew, I have to think. OK, that's bigger than low of j. We know that low of j is bigger than I. OK, this is saying, being a little messy here. Low of j is bigger than low of I in particular. And it's actually bigger than high of I. It's bigger than everything in I. Because j did not overlap I, that means that everyone over here that's in R does not overlap I. And that's what we wanted to prove. OK, if you follow all that. OK, think about this proof. It's tricky. But in the end, we get this nice result, right? Interval search works. We can find all the intervals that overlap we're looking for fast, all logarithmic time. Turn in your problem set. Problem set 6 is out today.